Hello, good evening everyone. Really excited. This is our 13th Vienna Deep Learning Meetup. Thanks for coming, thanks for being here at this very special location. For those who don't know, this is regularly on TV for the show Willkommen Österreich. We expected the stage to be a little bit bigger, but yeah. And we don't have a live band here, unfortunately, tonight. Sorry for that. So I'm Tom Leedy. Here we have Jan Schlüter and Alex Schindler. Together we are the 3 hosts and organizers of this monthly meetup called the Vienna Deep Learning Meetup. Yeah, it's been exciting times. We started like with an expectation to get 10 people together. Then it was 30 at the very first meetup. Soon it was 50, 80, 100 something. And then in registrations, we hit the 300 people landmark this time. Not everyone has arrived yet, but let's see. And in addition, it's the first time also that we have a live stream on YouTube. So hello, all the listeners and viewers on YouTube. Hello. Okay. Very exciting program tonight. But before we see what's the program of tonight, I'd like to thank. So we are kind of a wandering meetup, so we change location. We're in a new venue most of the times, which is very exciting for us too. But we have for each evening usually a sponsor who provides the venue and some food and drinks, which is very nice because it's a meetup. It's meant to be also about networking, getting to know people in this domain, exchanging ideas and so on. So thanks a lot for that. And for the first time, we also have a streaming partner, so we thank the company Streamed for providing the stream tonight, especially Maria Vasilevich. Yeah, before I come to the Erste Group, let's do the agenda now. So we're going to have a brief introduction by Boris Marte from the Erste Group. And then it's our main speaker tonight who came from New York, Google Cloud, Yufeng Guo, who is talking about TensorFlow wide and deep, data classification the easy way, which is almost an hour, including question and answers. And then we're going to have a 30-minute break to refresh yourself with some drinks, snacks, and talking to people. And then we're going to have a second talk by Valentin Boreyko, who is talking about one model to learn them all, which happens also to be an interesting Google approach to deep learning. And the three of us, which are quite silent now, Jan and Alex, will have some time to talk later on when we do the latest news and hot topic section. This is a regular chapter in our meetups where we collect a lot of new stuff, and this time it's really a lot because it's been June since we had our last regular meetup, so it's exciting things that we want to share, and then we have still time for discussions and networking. Did I forget something? No. Okay, then I'll call Boris Marte on stage from our host of the evening, the Erste Group. And yeah, there's also other people to thank from Erste Group, maybe Boris will mention.
Yeah. Hi. Hello. I'm here representing basically the George team of Erste Group. I must say that we are very honored and feel very privileged to be part of this great event today here in this great space. For us this is definitely very exciting and interesting because we also work with open source components in George, Elasticsearch, for example. So we're very excited to get more knowledge today about where open source technology will lead us tomorrow. I don't know if you know George, but we are very convinced that it's the best banking platform around. And of course, I'm so happy that some of the team members of the George team are here amongst us today. I want to thank the Meetup people for organizing those meetups here in Vienna. We need definitely such an ecosystem in this city. We need the talents, we need the people. We're looking for talents all the time because I think that's the source, that's the real source. You can talk about open source, but the real source are the people behind open source, right? So we're very happy, and I really want to congratulate you and thank you for organizing this meetup here in the city. I want to make it short. I don't know if you know where we are here. We are here in St. Mark's, which is the former cattle market or beast market, I don't know how you want to put it, slaughterhouse of Vienna, so I hope you feel comfortable. I wish you some cutting edge experience and a beastie moment tonight, and I hope you will get all the inspiration you need for whatever you want to achieve in your life. And remember this, never dream too small. Okay, thank you very much.
Thank you very much, Boris. So thanks for starting the comic element for tonight. We knew we needed someone here to replace the usual cabaret that's taking place here. Let's be short and welcome Yufeng Guo here on stage, developer advocate at Google Cloud, especially for the topic of machine learning. And yeah, I'll hand over the mic. No, I don't hand over because you're already wired. So let's switch to your talk. And no, it's in the browser.
That's the other tab. I'm going to go to the top.
It's all fine. Okay, big applause for Yufeng.
All right. Thank you, Thomas. Thank you, everybody, for coming and having me here. I know, New York and Vienna don't seem like they're very close together. They're not. And so it's been very cool. It's my first time in Vienna, so it's been very cool seeing the city. Very beautiful. And as Tom said, I'm a developer advocate at Google, New York, and I focus on machine learning, and as a result, lately I've been talking a lot about TensorFlow. It's all TensorFlow all the time. And so today, my objective is to show you guys that A, TensorFlow is easy to get started with, and that you don't have to be afraid of it. B, that you can use this model that I'm going to share with you to kick off your kind of any data classification needs that you have, where you just want to kind of do a first pass, so to speak, of your data. Instead of just doing, plot it in a spreadsheet and draw a line and say, well, this is my best, first attempt, and then I'm going to go on to more advanced methods, you can just use this approach, and we'll see what that looks like. And C, I want to, the third thing is to show you guys how you can also use TensorFlow to deploy your models into production and have that scale in a kind of easy to manage way. So let's get started. This is a deep learning meetup. I'm assuming that we all know what machine learning is, so I made just one slide to just share with you my very brief definition of machine learning. And I call it using many examples to answer questions. And so we'll take that and we can split it, of course, into training and prediction, right? Training, showing those examples, and prediction, answering those questions. The important point I make about this is that training and prediction are both important, integral parts of machine learning. You can't really have one without the other, right? When you do all this training, and if you can't serve up those predictions to your users and answer those questions, then all that training is useless. And if you make a great scalable system that can answer questions for all your users, but your model is not so good because your training didn't work, well, that doesn't work either. So both parts are important. And so this aspect of machine learning, I think, is something to keep in mind in terms of it's a pretty long workflow. Right? We start from our data, and we have to end up with answering questions to users, and in between there are many steps. And of course, you can do both of these things locally on your machine or data center or in the cloud, and we'll kind of look at some of those options today. So as I said, I've been talking a lot about TensorFlow. And for those who are not familiar, actually, let me take a poll real quick. Can you guys raise your hands if you have, we'll start with, who has heard of TensorFlow? Oh, fair enough. Out of those people, who has deployed or run TensorFlow in production, whatever definition of production you want to say. So like either for work or personal production. Okay, so that's a good amount. And then who has done something with TensorFlow, like as little, just ran a little TensorFlow, downloaded and played with it. Fantastic. Okay, so some of what you guys are going to see today will look familiar, and hopefully I'll be able to kind of extend your existing knowledge base a little bit. So for those, well, you guys all heard TensorFlow, so you know what this is. I'm just going to move on then. And TensorFlow, of course, supports many platforms, including, and this maybe some of you aren't aware of, it also can run on mobile and IoT. So for those of you who like to tinker with stuff, there are runtimes available for Android, iOS, Raspberry Pi, and there are more coming. And of course, TensorFlow comes from the two words tensor and flow, meaning multidimensional array and a computational graph, such as this one. And again, we can move through these slides quicker because you guys are such a well-informed audience. Awesome. So TensorFlow runs on a distributed C++ runtime, right? So it's fast. But then you can write in Python so that it's maintainable. And TensorFlow has many, many layers of Python on top of each other to have a number of different levels of abstraction. Levels of abstraction, there we go. And you have to choose the level that is right for you. And this is an area that sometimes people get confused about, or they get mad at TensorFlow for, because they're usually because they're not using the right level of abstraction. A lot of times we'll start from the bottom because we're engineers. We want to understand how every little bit works. So we say we're going to start on the low level, right? We're going to control every single operation. We're going to wire up this graph carefully, piece by piece. It's going to be so much fun. It's going to be like building those giant Lego sets with 10,000 pieces. And then I find out there are some missing pieces and I can't finish it. And that's not very good either. So I would recommend perhaps starting on a higher level, if possible, because that will make the coding easier. And just like when you learn to drive a car, you don't first learn how the metal is melted down and created and then manufactured, how the gas engine works, how the steering control system works, right? You get in the car, you learn how to drive, and if you're interested, if you care, you can learn more about how to change the oil and replace the parts that get broken. So you can use some of these higher level libraries to get started with TensorFlow faster and get real results. And this also has the benefit of incorporating existing best practices so that you have safeguards against kind of any mistakes that you might make. So that's kind of where we'll be operating today, as the high level kind of models in a box that take care of everything for you. So a super quick peek at some code. This is going to look really familiar, probably, to most of you guys, right? We're going to be working with kind of the pre-made models that you can just configure rather than build up from base blocks. And the piece that you will pay attention to for now is this inside piece, right? So this is a deep learning meetup. So this is making a deep neural network, DNN classifier. And you can create it by just passing in arguments rather than creating every single layer by hand and then wiring them all together. And so we'll see how that fits together shortly. And then for those of you guys who are already very familiar with deep neural networks, you might see this and say, well, I have lots of things I want to configure. Right? When I wire up my custom neural network, I pass in specialized optimizers. I pass in specialized activation functions. I have regularization. Where can I get all that? I'm going to have to go down to a lower level of TensorFlow, right? And what I would say is that there are a lot of options that you can configure with these calls. A lot of optional options. And so, you can do quite a bit before you're kind of forced to go to writing a custom model. And even then, it's not necessarily as much work as perhaps it sometimes seems. So that's enough code for now. We'll come back to that. I have a brief story. This is kind of to help set up for this quote-unquote wide and deep model. So let's say we're making a new startup. Okay, it's going to predict what users want to eat. It's a very original idea, right? No one has thought of this before. So say our users would say something like, I want to have fried chicken, right? And so then the app would think, and then come back and say, I will deliver you some chicken and waffles, right? And that would be ideal. But you say, I am a startup, so I'm going to launch and iterate. And so the first version you launch is just naive text matching. You just take the words that the user said, fried chicken, and you look up in your big menu of words and you say, what items have the word fried chicken in them? And you give them chicken fried rice. Right, so not exactly fried chicken, right? When you think fried chicken, right, this is not what you think of. And so that's okay. You say, this is my first version. So you iterate. You say, I'm going to put out my V2. And you reach into your deep learning, well, not deep learning, your machine learning toolbox, and you pull out linear regression, right, which memorizes your user's preferences. This is kind of like the classical approach to machine learning from, before deep learning became a thing. And so with that, you stop delivering chicken fried rice and you start giving them chicken and waffles when they ask for fried chicken. The problem is, it happens every single time. Every single time they say fried chicken, they get chicken and waffles, over and over and over. And so, then you get this feedback, the comments in your app, not so good. You get these 1-star ratings, people saying, stop giving me all this chicken and waffles. And so you say, okay, I'm going to iterate again. I'm going to put out a V3. V3 is going to have deep neural networks. Okay? And with that, you can use deep neural networks to create generalized recommendations. What's nifty about deep neural networks is that you can use what's called an embedding space to create spatial relationships between your menu items in this case. So when we had a linear network, the menu items were basically stored in a giant array. So let's say we had 1,000 food items. They would be stored in an array of length 1,000, one food item per spot. And you just have all these foods that are next to each other. And the distance from one food item to another food item in this array has no relationship with each other, right? If one food is 5 spots down, what does that tell us about the food that's 10 spots down? Other than maybe if you sorted it alphabetically or something. It doesn't really tell us anything about the food items themselves, right? How they're related in terms of their meaning. So with an embedding space, you can get this spatial relationship where similar foods are close together and more different foods are further apart. So this allows you to look in a cluster of this space and say, oh, you want fried chicken? Let me look around here, and we have a couple of different options here. Fried chicken, maybe I can give you chicken with like fries or something instead of chicken and waffles. And similarly, you have another cluster over here that has like lots of fruits and things like that, and maybe there's some cake over here, and then fruit cake is in the middle between them. And so you have this space, and usually this space is going to be more than 3 dimensions. So I can't visualize it completely, but that's the idea: is that similar things are closer together in this higher dimensional space, and more different things are further apart. However, sometimes you can be too general, because sometimes your users will ask for something like a hot latte with whole milk, and you deliver a iced latte with non-fat milk. And so then they say, well, this is, while similar in your deep learning kind of embedding space, it's different, right? And so how can we balance these kinds of requests? Sometimes when the user says something like, give me Italian food, give me fried chicken, like that's a general request, and you need to be able to generalize. But sometimes they ask for something specific, and you need to remember, oh, when they say they want this thing, they really just want this thing. And so, I guess now a little over a year ago, Google Research published a model called Wide and Deep, combining the linear network and the deep network together into one model. This is notable because it's different from previous approaches of combining different models, which are called ensemble methods, into a system where you actually train a single model that produces an output by itself, one output, instead of kind of multiple that you kind of aggregate in some averaging scheme. And so this means that the model can actually learn which side to use on its own. And intuitively, you can think about the way this structure works as the deep side doing a reasonably good job at generalizing to most of the requests, while the wide side memorizes the exceptions. So it memorizes the particular things that the deep side was not doing so hot with. And so that's kind of my transition from story to more science, I guess, and the end of my little story. Okay, so what I want to do now is we'll walk through a more real example with code, right? Like, fried chicken and all this food stuff. Hopefully you've all had dinner. This one is about US census data. So really it's just a toy data set, right? So the point here is to go through the actual code and the paradigm of working through it, not so much the actual data or the results themselves. So this particular data set is, the task is to predict classification, whether the household income is above or below $50,000. And of course, the task might be not just 0 or 1, it could be 0, 1, or 2, or 3, or 4, right? Like classification can go more than just 2 classes. And so our data set has a couple of columns. This is kind of your standard structured data problem, right? Whether it's logs data, user activity, whatever it might be. I'm just using census data as kind of the placeholder. And so you have kind of the standard columns: age, education, occupation, gender, what relationship they're in, and then of course, finally, this income bracket. And as we can see in this particular case, income bracket is not 0 or 1, but rather a string, greater than 50K or less than 50K. So we'll do a little pre-processing and get that sorted out. And of course, you could also do this beforehand. You could pre-process your data, generate zeros and ones before you feed it into any network. So a lot of options there. Okay, so one thing I want to point out is that these columns are, some of them are categorical, meaning they have like very well-defined values, typically strings, and some of them are continuous, numerical, real numbers. And so one way to think about it is that the wide side will kind of, a lot of the categorical stuff will go there, the continuous side will be treated by the deep network, and there's a little bit of crossover that we'll also check out. So the typical structure that I use to kind of approach thinking about the program structure is to load in the data, then set up what are called feature columns, and then we create our model, run our training, run our evaluation, run our prediction. So loading the data, in this case, I'm just going to load it in with pandas. Oh, I'd be interested. Another poll. Who uses pandas? Okay, let me flip that around. I had a feeling this might happen. Who doesn't use pandas? See, now people are shy. They don't want to raise their hand to admit they don't use pandas. But pandas is just a kind of one of the more popular data processing libraries out there. It has nothing to do with the animal pandas, just in case you were wondering. Yeah, I had to look that up too. I was like, I wonder where did this come from? And so, I'm using pandas to read in the CSV file. You can, read loading your data through lots of other means. And yeah, so once we have that loaded in, one of the cool things that TensorFlow has added in one of the more recent versions is this notion of some of these pre-built input functions. So input functions are TensorFlow's way of letting you control the data being inputted into your model. So if we have our mental model of how TensorFlow's kind of program structure looks like, you have your model over here, okay? And then over here is, let's say, your data set. And in between, there are two things. One is your input function. The input function loads in all of the data from your data set and then pushes it out in a format that is pre-agreed upon, kind of just features and labels. And then on the other side, you have your model. And at the head of your model are a bunch of what are called feature columns. So the model is just the actual structure, in our case, let's say deep neural network, right? So it's just the layering structure. It knows nothing about the actual input layer. So you could think of it almost as the input layer to the model. Here we'll call them feature columns. And so the input function, right, which loads the data in, that will push into the feature columns into the model. So in this case, the pandas input function kind of is a pre-built one that will take care of it for you. Yeah. And then, so next, we got to set up those feature columns, right? So once we have our data loaded, we have our input function, then we set up our feature columns. And feature columns is really your opportunity to play with the data, and there's a lot you can end up doing with feature columns. First, we'll set up our categorical feature columns, or sparse feature columns. And there are two options here. Well, there's actually a lot more than two. There's two I'm showing you guys here. One is called categorical column with vocabulary list. So that's where you know all of the possible values, the possible vocabulary list, right, in your data set for a given column. So for columns with very few options, this is useful. You can specify, I have this volume, and this value, and this value, and that's it, right? And then for columns that have a lot more possibilities, like in this case, the data set, the education column has, I think, like 40 plus different values. So you say, okay, I don't want to type all of those out by hand. Maybe you do, you can paste it in, that's fine. You can even load in a file for a vocabulary list. But you can have categorical column with hash bucket and just have TensorFlow take care of hashing all the values for you. Once you have your categorical columns sorted out, it's time to do the continuous ones. Those are a lot easier. You just use numeric column, give it a name, and you're done. These names are significant because they need to match the values that the input function will generate. So in this case, they are the names of the columns of the data set. Click. Okay. And so then what we can do now is we can play around with some of these columns. So you do this for all the columns, and now we can do transformations. One transformation is you can take a continuous column and transform it into a categorical one. So the first example here is a bucketized column. You can take a existing continuous column and divide it up into buckets. So for age, you might say, you know, I actually don't want the model to care about age at the granular level of, you know, 18, 19, 20, 21, 22, but in fact, maybe I care more about age ranges in this case, 18 to 24, 25 to 29, things like that. And then similarly, not similarly, sorry, now you have the bucketized column results in a categorical column. So we've turned a continuous column into a categorical one. So this allows you to also do crossed columns. You can take multiple categorical columns and cross them together. And I don't have that on the slide here, but you can actually use age buckets as one of the columns to cross. So you can take a continuous column, bucketize it, and cross it with other columns. So you can begin to see that these like one-line transformations allow you to do quite a bit pretty easily. So it's really quite nice. And then finally, you want to make sure you do the embeddings for your categorical columns as well, so that they can be passed into the deep side of the network. So now what ends up happening is you can take the continuous columns, turn them into categorical ones, and you can take the categorical ones and then embed them and kind of turn them into deep representations. So they then show up on both sides, allowing the model to kind of learn from the full data set rather than being limited to only the type that they're typically associated with. Right, so this was that. Okay, so let's look at the code for creating your model. And that's kind of one of the nice things about this high-level API, the TensorFlow.estimator library. The wide and deep research model is implemented for you as the DNN linear combined classifier. Take a breath, it's long. And you can just pass in kind of what are pretty standard arguments for the estimator library, which is model directory, just a string path to store the artifacts of training. Then you have, in this case, two more arguments here, linear and deep feature columns. Typically you have one or the other, but in this case we have both. And then we have deep hidden units. So the hidden units are the layers in your network. So that's, in this case, I have a 4-layer network with 100, 70, 50, and 25 neurons. If you want to change it, it's as simple as just changing the value in the array. You don't need to rewire anything. You don't need to, delete really much. If you want to make it only 3 layers, then you just take one out. So it's really great for experimenting with network structure. So once you have your model created, right, and you'll notice that when we created this, we passed in those feature columns. So now the feature columns and the model are glued together, and we've saved that in this variable, in this case just M for model. But the input function that we created earlier hasn't been introduced yet, right? We haven't glued that part in. And so that will show up next in the training loop. So when we do the training, we pass in our input function as an argument for training. So that's how the two sides come together. You have your model and feature columns, and then you throw in this input function. So that allows you to choose different kinds of data sets against the same model. So in this example, we see I'm using the same M to call training and evaluation, but I'm passing in a train file and test file for different inputs. So you can input different files into the same model and do different things with it. So that flexibility is nice. And then finally, when it comes to predictions, you guys are probably tired of seeing this now. It's the same thing. You call .predict, you pass in the input function, and in this case, the input function is just going to be a couple of values that you want to do prediction on, and the pandas input function again comes in handy where we can kind of specify these different parameters to control the input pipeline. Okay, so normally if I'm presenting on my own laptop at this point, I would go through the code. Let's see, how are we doing on time? Just want to check. We're okay? Okay, so let's see, assuming, this link should work. So what I did was I created a gist, and assuming that this keyboard works the same way as the US keyboards do. Okay, great. So what I did was instead, normally I would run this in a local Python Jupyter notebook, But instead, we don't have that. So I ran all the cells and then uploaded it to a GitHub gist so we can see the outputs even though I'm not running it live. So in terms of turning those slides into real runnable code, there's a few more steps involved, but basically, we import TensorFlow, import NumPy and pandas, and so one of the things, I'd like to call this out, is that I typically will click. There we go. I will typically print out the TensorFlow version as tf.__version__, because different environments will have different versions, just to make sure you have the right version that you think you have loaded in. And it's a nice print statement, so you know the cell finished running. And then I have a bunch of globals to store in all the columns of our data set. And when I use pandas, I typically will do a little more than just load it in. So I'll read it in, and then I'll take a look at our data. So here, this gives us a chance to look at what each of the columns look like. And you can see that some of these columns are strings, while other columns are numbers. We can also see using, this scroll is fast. We can use .describe to take a look at some properties of our data. So we can see that, for example, age ranges from 17 up to 90. So the implication is that in 1994, nobody in the United States was over age 90, which seems odd. I assume it's because of the way they cleaned up the data. Similarly, we can see here that, for example, the hours per week that people worked, nobody worked more than 99 hours per week. It's good to know. And nobody worked less than 1 hour per week. I don't know who's working 1 hour per week, but that's nice. So you can see some funny things there, and then we can describe on the categorical columns, and we can see things like native country has 41 different unique values, occupation has 15. We can see which ones are the most common, and we can also see that certain ones have very few values, like relationship only has 6 different values, marital status has 7. And then I also will usually do a cross-correlation across the columns that I can, just to make sure there aren't any columns that are very similarly correlated, because then if they're both in the data set, that will over-strengthen a specific signal, right? Because you have basically two columns that are essentially the same. And so we can see here that our columns are all pretty unrelated, so that's good. So here we'll get the chance to see what it really looks like to implement an input function. What I typically will do is I will create a generate input function, because otherwise you'll find yourself rewriting the same thing over and over again and only changing the name of the file that you're passing in. So in this example, I create a generate input function, and I take the file name and then a couple of inputs around the epochs, whether I want to shuffle and how big each batch should be. And those are essentially pass-through values that I will pass in here. I read in the data in my input function, and then I pull out the income bracket column. And I apply a short function to convert the columns that are greater than 50 as 1, and the ones that are not as 0. It's kind of a little bit of a hack, because then I cast the true false to an int to get the 0 and 1 out. And then I pass those x and y for the data frame and the labels in, and then the final 3 arguments we already talked about as just pass through. So what this will do is this generate pandas input function will take care of creating the appropriate input function that will just work with TensorFlow. So, if you can get away with it, I would highly recommend going this approach. There is an equivalent and essentially a same function called NumPy input function. So if you're working with NumPy, I'm not going to ask who uses NumPy. I assume everybody touched the NumPy at some point. And there's a NumPy input function, so it's the same thing. You pass in your NumPy array as your inputs and NumPy array for labels, and you can specify a batch size, how many epochs you want it to go through. Oh, also, if you put epochs none, it'll just keep going forever. Shuffle, true, false, it just saves you a ton of work. I've seen people write code where they're manually shuffling the data by selecting random integers to index into their data set. It gets ugly. So this is cleaner, it's safer, it's thread safe, all that good stuff. So yeah, take advantage of it if you can. Here we create the columns. So we saw the calls earlier in the slides, categorical column with vocab list and categorical column with hash bucket. I got tired of typing all the different columns, so I stopped. I just used hash bucket. If you have a data set that has like just a ton of columns, you could very easily, for example, loop through, right? You can just call a categorical column with hash bucket and just do all of them in your column, just generate the column names, C1, C2, C3, C4, etc. See, and then we have the continuous columns, much simpler, just numerical column and you're done. And then here we do our transformations, and I do have this example here where we combined not only this, we bucketized the column, but then I used this age buckets column that comes out, and I pass it in as a column that I cross. So that's an example of that happening. Go down? Nope, okay. Scroll. Okay, so then what we're going to do is we're going to take the columns that we had and group them into two arrays. So our wide columns are all of our categorical columns, along with all of our cross columns. So age buckets, education, occupation, and all these cross columns also go here. The deep columns are the numeric ones down below, as well as you can take all of the categorical ones and embed them. The ones with a lot of different possible values, like education and native country, use a standard embedding column. Because of the complex relationships between the many possible values, we want to put that in that space, right, and have those spatial relationships be preserved. For ones with fewer possible values, you can use what's called an indicator column, which is similar to a one-hot encoding, if you're familiar with that, but it's slightly different. It's useful for simpler data sets. Usually if you have like fewer than 10 values, you can get it with doing something like that pretty easily. And that's just like a smaller representation. You can use an embedding column if you want, but the problem can be that it can lead to less good representations actually, because with embedding columns, it's a learned representation, whereas with indicator columns, it's more hard-coded, so to speak. Okay, so when now we go and create the model, this is the line that we care about. This whole function kind of steps through the option of creating the wide model, the deep model, like separately. So you can kind of choose as an argument to this generator function, but it's, this is the one that we care about, and it's the same as what we saw in the slides. So not too much to see there. So when you run this particular cell, what you get is, we just create the model, right? But we haven't trained it or done much with it, so there's not really much notable here. It's just stored in memory. It's when you start running the training that you get something going. And so we see here that we pass in our input file. So you can see here our input file is our CSV, and we can pass it into that generate input function. So this function returns the pandas input function result, which is another function. And so that function gets called. Every time it gets called, it returns a new batch of data until it finishes and it returns an end of file exception, which the train function knows, and is expecting. And so it prints out all of our results, and we'll store kind of the artifacts into that path that we gave it. And then when we do evaluate, it's the same kind of thing. We pass in to here our test file, and you'll notice that I also specify number of epochs to be 1 and shuffle to be false, because when you do evaluation, you just want to run through all your numbers one time and then stop. There's no need to shuffle just because it's a waste of energy. And then we'll do our prediction. So here, what I did was I just arbitrarily chose rows 8,000 through 8,005 of the evaluation data set, just to kind of see the results, the explicit results for that. So I display the 5 values, and you can see here that the true answer is that it should be 0, 0, 1, 0, 0, right? Less than, and then the middle one is greater than 50K. And so when you run the prediction, here I just explicitly call pandas input function because my generator was expecting a file name and I haven't written these values to a file. So I'll just call the value directly and I'll pass in that small miniature data frame with just those 5 values that we just saw and say, pull one value at a time, go through it once, don't shuffle it because that would just confuse our results. And print that out so we can see here we got 0, 0, 1, 0, 0. So that's great. And you can also see the probabilities are also available there. And so for now, I'm going to go back to the slides and talk a little bit about TensorBoard. So when we did the training, you can see how the training is going via TensorBoard. So when you run TensorBoard, what you do is you run TensorBoard -- logdir, and then you pass in that same model directory that you had before. And then you go to, I've been meaning to add it to this slide, you go to localhost port 6006. And since this audience has used TensorFlow a lot before, I suspect at least somebody here knows why it's port 6006. Anybody? Don't be shy. Yes, it spells Goog, G-O-O-G. So you can let people know that, and then next time I ask, more people will know the answer. And so we can see here, it helps you visualize a lot of the parameters of your model, including, because we use that canned estimator, you get all these values for free, right? You saw my code. There's nowhere where I set up, plot my loss, make sure we output that. Plot my accuracy, plot this, plot that. It's like it just comes for free out of the box. So it's really handy in that sense. So across the top, you can see there's a bunch of toolbars. So the first one is the scalar values. Then going across, we have graphs. So this will actually show the graph, the TensorFlow graph that is running under the hood. And now you really get to see what the estimator library has done for us. Right? What would we have to do to replicate this result is create this crazy model, is wire all of this together. And of course, each of these blocks, is nicely organized for you, so it looks nice, but inside is more stuff. So if we click the DNN value here, and because we're not live, I've made slides for these, you get more cells inside of that, right? So there, if you look very closely and have really good eyes, you can see we have our hidden layers, 0, 1, 2, and 3. Okay, so that's TensorBoard. Now I want to look to the prediction side of things, right? We did a bunch of stuff with training, but as we said at the beginning, it's just as important that we be able to answer questions with our model. We need to be able to handle whatever the load might be for predictions. And the first thing we need to do in order to do predictions is export our model. So exporting our model with TensorFlow is another kind of model call. So it's m.export_saved model. I think I have it here as well. So it's the last final chunk of the code here. I screenshotted it for the slides. But basically, yeah, it's this bit here. And to do that, you pass in a path to export the model to, and a function called the serving input receiver function, or just serving function. It's the same idea as the input function, but it's for the serving side of it, for the prediction side, because you're not going to be likely processing a file with labels, right? It's going to look different. So it's just going to be the feature columns, hopefully, and oftentimes it's not going to be a CSV file, right? It's going to be JSON or some kind of protobuf. And so that's why there's a slight difference here. And this fell out of projection mode for some reason. Present. Okay. So when you run export save model, what you get, if you look at the bottom of the slide there, as soon as this thing goes away, okay, is you get these two file listings. One is the saved model.pb, and then there's a variables folder. There's two files in the variables folder. And these kind of 2 or 3 files make up everything that TensorFlow needs in order to serve predictions fast and at scale. In particular, the difference here is that instead of loading in the same graph that you were just using for training, this is a specialized one that's been optimized for serving predictions. Because when you're training, a lot of things are variables, right? There's all these update loops. I mean, you saw that graph from before, right? There's a lot of stuff going on there. But when you're just serving predictions and you just want to serve predictions as fast as you can, you don't need all that other stuff holding you back. So it cuts away all that. It takes the weights that used to be variables and able to be updated, it freezes them as constants, right? Because you're not updating them anymore. And so you have your training graph, and then you output a specialized graph for serving predictions. And so what this means is that you can continue training now. And when you get it to a better state, a new state, and you say, okay, now I want to output a new prediction graph, you export another saved model. And so you can put that into different folders, and you can have kind of V1, V2, V3. And so it really facilitates a nice workflow. And when you think about serving and what it takes to go from data to answering questions for users at scale, you have data, right? And then you have you guys with TensorFlow, and you output a model. And then once you have that model, you need to do something with it, right? Put it in some kind of server, be able to spin up a bunch of instances, do all that good infrastructure work that I know you guys all love to do. And then put some app in front of it, which is the fun part. And so this notion of having to create a system for scaling up machine learning predictions that is secure, has a nice API endpoint, dynamically scales up and down, that's like a whole other project on its own, right? We spent all this time working with our data, creating nice models, and then it's like, oh great, now I have to go work on this ops stuff. And there are whole conferences for ops stuff. So it's a lot to kind of take in. And this is what I meant at the beginning when I was saying that machine learning is a long pipeline. And a lot of times what ends up happening is you create the model in your notebook or whatever local environment, and you throw it over the wall to your data engineers or whoever is running the machine learning productionization of things, right? And they take your stuff and then they figure that part out for you. Oftentimes misinterpreting various things, and there's misunderstandings, and then there's lots of shouting. No. And then, so the problem is scaling, right? If we could just deploy our model, just throw our model into this bucket and just say, okay, we're done, right? I trained my model, I exported it, and now this little bottle will take care of everything for me. Wouldn't that be nice, right? This is the city of music, right? So you guys know what that is. And yes, of course, scale is running it on lots of machines. And one of the things that is neat about TensorFlow is that this exported model can go into TensorFlow serving. And TensorFlow serving is this other aspect of the TensorFlow open source project that oftentimes people miss because everyone is so focused on the training. And so TensorFlow serving is a fast C++ binary that you can load into your data center and run predictions using those exported models. You just load that in and you're basically done. For people who know ops stuff, this is very straightforward. But unfortunately, or fortunately, I don't know, this is a different crowd from the ops crowd. And so as a result, we're not going to go through TensorFlow serving so much, right? Though that is an option if you want to run it on your local environment or local data center. We're going to talk about the cloud and how we can serve up predictions from the cloud in a way that will scale up and down for you so that you don't have to worry about writing your own scalable system from scratch. So Cloud Machine Learning Engine is Google Cloud's kind of managed TensorFlow workflow environment. It does handle the training and scaling the training for you, but a lot of times folks have their own GPU cluster under their desk or in the closet over there, so they're happy to do the training on their local machine. Or maybe the data set's not really that big. You have a 2 gigabyte data set, it's on your local disk, you have a 16 gigabyte memory or 32 gigs of memory in your machine, and you're just like, why, the upload time is not even gonna be, it's going to be longer than it takes for me to train my model. So the other side of it is prediction. And this is where I think it really shines because you guys all want to spend your time with your data, not with ops. And so when people talk about machine learning engine, a lot of times they're saying, oh, scalable training, it's so great and stuff. But if you don't have many, many terabytes of data, a lot of times it's not super, super necessary, but on the prediction side, it can be a real lifesaver because it works just like TensorFlow serving. You export those model files, and you pass it in, and you're done. You get a auto-scaling, secured REST API that you can call from any mobile phone, any web server, IoT device, thousands of devices if you want, and it will just scale up. And then when all of your users go to sleep and don't need it anymore for the other half of the day, it will scale back down, all the way down to 0, right? And when it's at 0, you don't pay anything for it, which is great. So what does this look like, right? Creating a model and its versions, right? Because you're going to export multiple versions as you improve your model. So you have V1, V2, V3. And so the model now, then we can think of it as a encapsulation, right? It's an abstraction layer that just says, this is all the versions of this model. And so to create a model, you really just need to give it a name. So in the Cloud Platform UI, you just click Create Model, and you can do everything I'm showing is you can do also from the command line and from the REST API. So you can script it, you can bash script it, or call the API directly. You just give it a name, you click Create, and you're done. Right, so now you have a model. Okay, it's good. And so, of course, you want to create a version is where it really is interesting. So you create a version. And so say you call it V1, and what you're going to do is you point it at those files, right? Those 2 files, well, the file and then the 2 folders, the folder with the 2 files in it. And I've already uploaded those to cloud storage, so you pass those in. And so I just copy that path, and you can see those 2 files there, save model.pb and variables, and paste that in. One thing to note is there's I didn't highlight it, but at the end of that, where's the thing? Okay, here. There's an extra slash. Well, not an extra, there's a slash. It's very easy to forget to put the slash, and the UI will be very upset at you for not putting the slash because it's a directory, right, and not an actual file object. So don't forget the slash. And so once you say create, you wait a few seconds, and then it's created. Hooray. It doesn't feel very kind of dramatic, like a lot of things happen, but in reality, a lot of stuff has happened in the background, and you have a fully auto-scaling prediction API ready to go with your custom model loaded in. So it really is quite something that's worthy of note. And you can create new versions, right? You create V2, V3, and you can see over on the right-hand side, there's a set as default value, right? Because I only have 1 version shown here, there's only 1 default. But as you create more, you can choose to set a different one as default. It will not change the default value for you when you create a new version, right? Because maybe the new V2 you created, you want to test it a little bit first, right? So the default is just when you make that API call, you can optionally provide a version. If you don't provide that version, it will route it to the default version. But if you provide the version, you can now split test, A/B test, whatever you need to do to validate a new trained model before setting it as default. And this is the command line version. It's the same thing. The top cell is creating the model. The bottom diagram is creating the version. So once it's created, we want to make some predictions, right? So you can pass in JSON for the REST API, right? So this is an example of passing 2 requests for simultaneous prediction. And we pass that in, put it in a file. In this case, I called it census.json. And the command line tool also supports, doing this, so you don't have to write out the API by hand when you first play around with it. And the response is what you'd expect. The JSON looks like this. You get the probabilities, you get the classes, right, in terms of is it a 0 or a 1, and you get some other information around the actual network itself, in this case the logits and such. So in this example, we've seen how you can train a model locally, upload that file, that exported model, and put predictions in the cloud and let that just scale for you. It's worth pointing out that because of this file intermediary, right, you have this intermediate expression between training and prediction that kind of helps connect the two, you can flip these two so that you, if you wanted to train in the cloud, but then wanted to deploy the exported model to your local data center because of latency requirements, locality, things like that, you can do that as well. And so because TensorFlow is open source, because the exported models are this kind of standardized format, you can interchangeably move this back and forth. And of course, I guess I should also point out, obviously, you can do them both in the cloud. So that's pretty much kind of wraps up my portion of talking about TensorFlow and doing training, doing prediction, using the wide and deep network. And I really would want to emphasize that the wide and deep is super straightforward to use for structured data, to the extent that you should, I posit that you can just use it out of the box as just the first pass at your data. You know, oh, you got some data, just throw that CSV file in and see what comes out, right? That's your new baseline. Instead of running a linear regression or something like that, you can just throw it into wide and deep, and from there, kind of improve, you know, try to improve the model from there or tweak it from there, because like it's a really decent starting point in a lot of use cases because of that flexibility, because it can take care of a wide variety of data. And shameless plug here, I'm also currently producing a video series called AI Adventures, and it's up on YouTube. You guys, you know, feel free to check it out. Let me know what you think. You know, each week we kind of publish videos about, you know, TensorFlow, different tools. For those of you guys who haven't used pandas before, we'll have an episode about pandas. Let's see. Yeah, and I think this week we just released the latest episode a few days ago. Sat down for a nice interview with a colleague of mine on the Google Brain team who does research into natural language generation, not natural language processing, but natural language generation. Really interesting. I had a great time with that. So you know, do check that out. And so some other resources for you here: Cloud ML Engine, TensorFlow.org, and at the bottom there, wide and deep -census, that's the GitHub repository where the code that I showed you guys tonight came from. And oh yes, and I'm on Twitter at Yufeng Guo. So if you guys have other questions, want to show off cool projects you guys are working on, you know, feel free to you know, tag me, message me, whatever. So with that, I'll you know, turn it back over to your lovely organizers. Thank you.
Thanks a lot, Yufeng. That was great. I hope everyone benefited from what Yufeng presented us. And like, who of you thinks you can start training a deep learning model tomorrow?
Who already trained deep learning models today? Was already.
Who of you is going to start training a machine learning model within the next hour? No, just kidding. So this is time for questions now for Yufeng, and we're going to open up questions also on the YouTube channel. So if there's a live chat, so just put some questions there. We're going to check and select, let's say, a few of them, the best ones, to be asked here too. Alex will point me to those, but let's start first with questions from the audience here. So who is having a question? There is one.
Hi. So I wanted to hear maybe a bit about your Jupyter notebook workflows with Google Cloud or the Google Machine Learning Cloud. Like, how do you integrate your notebook workflow? Like, do you run it there? Can it somehow connect to these models that you deploy to the Machine Learning Cloud and stuff like that?
Yeah, that's a really good question. I would show you, but this is not my laptop, so I'll try to talk through it as best as I can. One thing I'll point out is Google Cloud also has a product called Data Lab, and so Data Lab is basically hosted Jupyter notebooks. So you just go there, you create a notebook environment for yourself, and you can just run it in the browser. It's running on a compute engine instance in the cloud. It's not tied to your local machine at all. This can be useful, especially when you're, say, provisioning it for larger groups of people. For those of you guys who are, you know, in companies and in positions to like be thinking about those problems. With regard to running it against kind of the rest of Google Cloud, you know, within Data Lab, one of the nice things about Data Lab is that it comes with a number of integrations with the rest of Google Cloud, as you would expect. So for those of you guys who are familiar with BigQuery, which is the cloud's data warehousing solution, so that's a great place to just like dump your data, logs data, whatever data, and you can pull that out with SQL. And so that integration is very tight, and you can create training jobs on machine learning engine from Data Lab directly. On the kind of local Jupyter notebook workflow side of things, I typically run Jupyter notebooks as truly, I view them as just for prototyping. So it's for experimentation on my local machine. A lot of times I'm doing this on the airplane and things like that, so I'm not going to kind of be connected to the network. But I've seen some workflows where people will use the Jupyter Magic, like write file, and have a cell that has their source code, right, for like different codes, and then they will run the cell, write the file, and then they'll have a cell after that that does bash and calls the command line arguments. And so that's kind of a hacky way of getting around it, but like it works, and it does absolutely put all the code in one place. It's actually kind of nice because sometimes if you just provide the source code, it's like, okay, now how do I actually execute it, right? But now the notebook contains that part too, and you can set up environment variables as another cell that you can provide those values. So the workflow, I've been surprised at how well that works. Typically, what folks will do is they'll just use raw Python, right? They'll just have go into your favorite editor, have Python file open, and then you just have a Python script rather than running cells one by one, because especially on the training side, which I assume is kind of what you're getting at there, you're not going to be running kind of a live execution environment. Though with Data Lab, you kind of have that, right? You can provision a beefier, stronger machine with lots of RAM and lots of memory, maybe hook up a GPU to it, or a couple of GPUs to it, and then you can do some real powerful stuff in an interactive environment. So you have a couple of choices there.
Nice. Are there more questions here? I guess there are, yeah.
Hi. So my question relates to the input pipeline, and basically TensorFlow is this interaction between the Python and the C++. And for me, it's a bit obscure, like where my data is. And for example, I would like to maximize the time of my data being on the C++ side and avoiding copies from the Python to the C++ over and over, so that my GPU is not starved of data and can really optimize the runtime. So do you have some advice on how to make sure that your data is on the right side of things?
So when it comes to kind of loading data in, the next kind of iteration on input pipelines is the datasets API. And so TensorFlow 1.4 release candidate 1, so first they do 0 and then 1, came out yesterday, I want to say. And with 1.4, we see the datasets API moving into core. So tf.data.datasets allows you to kind of specify these input pipelines. It's a much better solution than some of the scalable solutions that are currently available. And basically, you have a bunch of kind of, it's your standard like dot operation pipeline values. And what that will do for you is it will build up in your TensorFlow graph, right, which runs in C++, all of the operations needed to pull your data in, any mapping operations, shuffling, changes to the data, and then straight into the training, right? And so that'll definitely, that's one way to keep as much of it into the C++ as possible. I know in my example here, we see a lot of kind of Python, right, being written, but it is executing in C++. It's just that with pandas and NumPy, it really only works when you have data sets that fit in memory. But when you have data sets that are larger, the datasets API really helps with that because it supports streaming in data. And when you do distributed training, what you really want is your files to be sharded and coming into your workers, right? And so you have the model distributed across the workers. So each copy of the model that the worker has, wouldn't it be great if that graph also had the data processing piece as part of that C++ model? And so you have that. And so yeah, absolutely. I think basically everything is moving to being in C++ while still keeping that Python readability high. One of the big focus points of the TensorFlow team for the next kind of year really is improving the usability of TensorFlow. A lot of the low-level TensorFlow code that is out there from the past, say, year, kind of showcases a lot of possibilities, but it does get kind of complex, right? And they really want to make it easier to do the right thing. easier to do what you want without having to create, crazy workarounds or really complicated Python code.
Alex, do we have questions from the YouTube channel?
Yeah, there was one question, and it was, what will be the use cases for deep learning in the next decade? Well, it's kind of a generic question, but what are kind of the visions from Google side where deep learning will lead us in the future, where Google will lead us in the future?
Yeah, because I was going to say, next 10 years of deep learning, I feel like, you guys might have some thoughts about, use cases for deep learning. But in terms of, where deep learning is kind of going and what it is capable of, I'd like to actually expand it a little more to, the broader machine learning and AI field, because when you kind of boil it down, this is something that Ian Goodfellow, who invented generative adversarial networks, he said the deep networks are really, at the end of the day, a function that maps from inputs to outputs. But it still is just a function. The end result isn't nearly as clever as we sometimes hope or think it is. When we say, oh, my convolutional network, recognizes this cat in an image, right? It doesn't know that it's a cat, the same way that you or I, in our brains, we as humans can see this and say, yes, I know this is a cat. And for the network, all it's doing is it's mapping those pixel values through the function, and cat happens to be what comes out the other side. And you can see this in a lot of the now what are called adversarial examples, where you can take a picture. The classic example they had in the first kind of research around this was a panda. And they took the network representation of a gibbon, which is like a monkey, and they overlaid, and now it looks like, it really just looked like static. There's like colorful purple and red static. And they overlaid the image, and the resulting image looked the same. It just looked like a panda. But the network was like 99% sure it was a gibbon, that it was this monkey, even though it clearly wasn't, because at the end of the day, it's still just a function. So, I think the limitations of deep learning are definitely becoming more and more apparent as the field develops. And I think it really will push researchers to both improve on and expand the capabilities of existing kind of technology, but also look to other areas and other aspects of machine learning, and how it can be used in collaboration, in partnership with the deep learning techniques of today and tomorrow.
Very nice. I was recently at the World Summit AI in Amsterdam, and it was a huge discussion topic also whether deep learning will lead us to artificial general intelligence and solve all the problems of the world, and the view was very much this one. Do we have more questions here in the audience? Anyone? Yeah, over there. Can you raise your hand again?
Yeah, hi, thank you for the talk. And I was wondering, I'm experiencing with cross-validation, which is maybe not too common for deep networks, but how do I reset the weights after each loop? Is there a possibility with the network you showed, or do I have to dig deeper into the TensorFlow code? Because I realized it with Keras that he does not reset the weights, so basically right now I'm loading the weights in every loop again. And I was wondering, if I go down to TensorFlow, is there a possibility?
When you say you want to reload the weights, just to be clear, are you saying you want the values to be kind of set back to the original untrained values?
Yes. Or a new initialization?
I think the question is, you do a cross-validation, so in each validation loop you need to restart with a random model again. And I know that in Keras you cannot just say model reset to get a starting point
You
again.
basically have to create a new model.
It, yeah.
Yeah, I'm not aware of any way to reset, at least at this level of the API.
Okay.
You mean you could obviously grab the graph and just reset the whole thing.
Okay.
But like, yeah, TensorFlow definitely allows you to kind of reach into the box and play with it. But there's no like easy API that I'm aware of. That's a really good use case though.
Yeah. You can't just say reset yourself and start over, right? You can't.
Not that I'm aware of. Yeah, because what it'll do is it'll load in the checkpoints, right? So those checkpoint files that come out, it'll just load those in. Those are the weights. I mean, you could delete the checkpoint files. That'll do it. That'll definitely do it. So you could delete the checkpoint files and then, so do you really, when you're doing this, do you not care about the result? Like you got the result, but you don't care about the weights anymore? You just got the
result. Right, you only need to start over with the next.
You start over with the next one and you don't need to preserve those outputs, the weights?
Just
I am kind of now preserving only the predictions, so to get an average about all the cross-validation loops. But so far, like, there is the possibility to save the model, then reset the weights, train again, save the model.
That's a really good solution, though. You can just take the checkpoint files, copy them somewhere else, so you have them, or, well, not copy, move them somewhere else. So now that folder is empty. So then when it starts training again, it's going to look in the folder, and it's going to say, oh, do I have any model here to pull in the existing weights from? Nope, no weights here. Start from scratch.
Will it do a new initialization or use the same one as before?
Ooh, now we're getting into the...
Because this is really like, I have that same problem, especially when you do scientific evaluations, you want to cross-validate to have stable results.
Yeah.
But if you start over with the same weights again, maybe
not as useful, even though you've changed it to a different chunk of the data.
What I do is to recreate the entire model. It takes some time, but you're sure there is a fresh model.
Yeah. Interesting. Yeah. So I think moving the files out is definitely a good start. But in terms of resetting the random state, yeah, that part I don't have the code base memorized, unfortunately. So you may have to dig into the source code for that, or I can ask.
Maybe
I can ask some of my colleagues. Yeah.
Take this.
Yeah, that's a really good question because setting random state at various points in TensorFlow, like there are certain things that are really good at making sure that the state gets cleaned up after each one, and some things that are not as good. So I don't know which one this one falls into. I'll look into that for you, yeah.
Would be great, yeah. Thank you.
More questions? Don't be shy, yeah. Alex here. Are you asking a question or YouTube?
Yep. The question was, have you heard about Uber's new distributed TensorFlow framework? And the second part of the question was, why do we need this, and how difficult would it be to set it up with vanilla TensorFlow?
So let's see, I have heard of it. I haven't had a chance to look into it too much, unfortunately. So I don't really know how difficult or easy it would be to set up that framework with TensorFlow. I mean, I know TensorFlow already has its own kind of distributed training system in place, so you don't really need another framework on top of that, I guess. Yeah, so TensorFlow's existing distributed training should do the trick. If you're, if you're interested in setting up your own distributed training, which it sounds like this person is. Yeah, I don't know if you have any thoughts on that. Have you heard about this?
Not in detail.
I think it starts with the H, but I can't remember the rest of the name.
Maybe one more question here. Anyone? Yeah, here in the front row.
I have a question about...
just a second, you'll get the microphone.
First of all, thank you for a nice talk. And I have a question about more tools to image classification or some kind of additional, maybe you have a new convolution network or whatever, to introduce a new version 1.4. Because I'm not heavily take a look about what's new inside.
Did you say you were asking specifically about convolutional networks?
Yeah, something new, yeah.
So with 1.4, one of the interesting things, let me ask you, do you use Keras?
Yes.
So you have existing convolutional networks set up in Keras?
Yes.
Okay. So one of the cool things that are coming out in 1.4 is that the version of Keras that is embedded inside TensorFlow, tf.keras, is getting a extra function added on called the keras.getEstimator. Okay? And so the call that I made that did tf.estimator.dnn linear combined classifier and made that model, you can now replace that with whatever your Keras model is, right, written in Python, presumably loaded in from another file or loaded in from another, and do .getEstimator. And it will basically convert the Keras model into a TensorFlow estimator. And so you can just drop it into your existing, that workflow, and it'll just work. So what you get, what's great about that is that you get distributed training. That's like the big win, right? Because Keras doesn't support distributed training, but if you convert it into estimator, now you can do distributed training. And you can do that, so in 1.3, you had to wrap it in a custom model function and make a custom estimator, but now they've taken away that hassle, and now you can just call getEstimator and be done. And so that's really a huge win, because that opens up the doors to, not just distribute it on CPUs, but distribute on GPUs and all that stuff, because the estimator framework packages that all up for you. So no real news on the, prepackaged convolutional networks, but hopefully using getEstimator, you'll be able to take advantage of your existing code base, which maybe is even better than writing new code.
That's the point, actually. Very nice to have Yufeng here to get first-hand tips and tricks for such things that you would need a lot of time probably to find out yourself. So really, really nice. But I have a little detailed question on the data pre-processing, actually. Can you explain what's the benefit of doing those age bins, the age groups, and then also cross it with, what was it?
If you just cross it with
other
different
categories.
Values, So bucketization and feature crosses. Bucketization is useful when you have a continuous column that you want to break up into kind of segments, right? And you want to basically say, this segment, I care about this segment, I care about this segment, and you can just give the border, the boundary values, and it'll just generate these kind of buckets for you. Now, obviously, you could do this, right? We could all write Python code to pre-process our data file, right? Put a new column in that says, 0, 1, 2, 3, or 4, or 5, depending on which bucket it falls in, and have that map to the value. But it's a little bit of hassle, and we could do it, but this is a one-liner. It gets embedded with the C++, becomes part of the graph. There's a lot of advantages to doing it that way. And in both cases, though, you can now cross that with other features. So a crossed column, if we go back in the slides a little ways, I kind of glossed over this point because I kind of talked past it by accident. Oh, there it is. Yes. So this is kind of my loose conceptualization of a feature cross, is that sometimes, if you're lucky, your data looks like the value on the left. Blue is on one side, orange is on the other. Draw a linear fit. Good job. But sometimes your data is not so nice, right? It looks something more like the picture on the right. And in those cases, you end up what you can do to kind of resolve that is using a feature cross. And what it does is it considers the notion of kind of X and Y, I shouldn't say X and Y, A and B, like this column and this other column. And that allows you to, it's like multiplying the columns. It's like A times B. Yeah, it's a tough one to conceptualize, but basically it allows you to unstuck these two groupings. And so sometimes with certain relationships between columns, it can be useful to consider this column and this column together rather than considering them independently along with all the others.
Isn't that a thing where you would assume a neural network to find out itself, or do you think it's really beneficial to do it manually beforehand?
So with this particular situation, like when you embed the columns, right, because these are wide columns, these are categorical ones. So you pass them into the embeddings, and classically, not classically, I guess, but like it's getting to the point where it's classically, the deep network will take care of that for you, right? And given a big enough network with enough data and enough training time, yes, it will take care of it for you. However, if you already know that there's a relationship between these columns, then make your life a little bit easier. and put that in. You know, don't kill yourself to like come up with every single possible thing. But if you already know there's a relationship, and this is, I think, the human element of data science, right? Is you can bring the unique insight from your domain-specific knowledge around the problem that you're trying to solve, and that can really kind of boost your model, so to speak, you know, because what ends up happening is these columns, the cross columns, go into the wide side, right? They're categorical columns. They'll go into the wide side directly, and you know, that's just a linear model, and so this will just help improve the linear model half of the wide and deep model in this particular case. Yeah.
Got it. Thank you.
Yeah.
One last question, or should we close? Yeah, you have the microphone still, so.
Yes.
Good.
My question is about the standard open neural network exchange, and when you standardize the models and the weights. Facebook just Facebook research introduced this stuff. How you think it will be implemented in TensorFlow, or we can see in nearest future that we can build something in PyTorch and export it and use it in TensorFlow.
Is this I'm not familiar with this particular one, but is this similar to like the Onyx data format and like all these different ones that are? So yeah, I mean, this is definitely a kind of a open question right now, right? Is your classic, there are too many standards, I will create a new standard to unify all the standards situation, and you know, I don't really know kind of where that's going to end up. I mean, obviously, you know, we have this existing situation where Keras is acting as a little bit of a bridging language between lots of different libraries, and the exported models from TensorFlow, for what it's worth, are, you know, not super proprietary. Really, they're just protobufs. They're basically yeah, it's equivalent to like JSON, but like more compact. So there's no like, you know, it's not, yeah, it's not a special binary structure either. So I don't know. It'll be interesting to see kind of what ends up happening with all these different formats. I would assume that, you know, at some point there will be interchangeable kind of dialogue between all the different libraries. Yeah, thanks.
Okay, thank you very much, Yufeng. Let's thank our speaker, Yufeng, again, who made all the long way to come here and share his insights firsthand about TensorFlow and Google Cloud. We're going to do a 30-minute break now, which you can use to network. I guess, Yufeng, you will be here for more questions maybe for people?
Sure. Yeah, and Alex has helpfully distributed some, I should have saved one so I could show what it looks like, but I brought some TensorFlow stickers, and they're distributed among the tables in the back, so nice. Please help yourselves. And yeah, so refreshments, snacks here in the break. In half an hour, we're going to continue with the second part of today's meetup. It's going to be one model to train them all. To rule them all.
To rule them all.
No, I don't know what's
by Valentin Boreka. And the latest news and hot topics section presented by us, the organizers. Okay?
One model to learn them all. Yeah.
Oh yeah, and for all the people watching or all the people here also, you feel free to share the video stream. This is a premiere for us. So spread the word so people can also watch online. It's not only live. You can watch it later on as well. Okay, thanks.
The link.
Great.
At the Viennese AI Summit, the most well-known researchers and practitioners get together in order to exchange new ideas and discuss the diverse application fields of artificial intelligence.
We had 450 people here in the audience and 5 fantastic speakers from Google, Facebook, Dane Studios, Zalando and Johannes Kepler University.
The goal is to go beyond the hype and gain a practical understanding of artificial intelligence its potential, as well as its underlying algorithms.
AI is what hasn't been done yet. So the term is changing constantly. What used to be AI is nowadays just considered algorithms.
The constant progress is fueled by more efficient algorithms, faster processing power, and an exponential growth in data.
It's already happening in everyday life, like self-driving cars, live translation on your phone into like 100 different languages. Like this is really true benefits for mankind, and there is much more to come that improves our daily lives, like of all the people.
And I think that machine learning has the opportunity to, fundamentally change how software is brought to market, and to improve both how people live and how they work. And I think we'll see, we're just really at the tip of the iceberg right now. We'll see over the next few years broader and broader implementation of machine learning in really everyday tasks.
Since the range of applications broadens, the demand for experts increases. Ongoing developments need to be reflected and embedded in business education.
For businesses will be challenged and will change because of this digital transformation. So we need to educate students in fields like data science. So we need educational systems that also bridge these gaps, so to bring the technical nerds with business people together.
I've been working as a data scientist for 7 years abroad and returned back to Vienna, and I felt like there should something be happening actually in Vienna.
Europe should step up, and the universities also really start training people in AI, data science, machine learning, and also in the overall data, like big data engineering, this side, to be able to respond to the growing needs of the industry.
As self-learning machines outperform humans in decision-making at an increasing pace, some might express concerns. Do we have to be afraid of machines overtaking the world?
I'm not afraid that AI takes over the world very soon.
The reality is we're pretty far away from systems being so smart that we have to fear them.
Thanks to this AI Summit and the monthly deep learning meetup we're doing, it's not a complete black box. So some people say you can't really see inside what the machine is doing. It's not really true. If you learn to understand AI, you're less afraid of it.
The experts predict a bright future.
The things that machine learning, at least at the beginning, are certainly going to focus on are things that A, you're not good at, or B, you don't like doing.
If there's a future where people can be happy with what they're doing and feel inspired and not have to do these things, and these things could be automated, that sounds incredible.
We've had a 45-minute break. Hope you enjoyed and made new contacts, exchanged important information. Yeah, I'll walk quickly through the rest of the agenda. So our next speaker here is Valentin Borrico. Do I pronounce your name correctly? Right. Yeah. And he's presenting his lightning talk about one model to learn them all. Gonna hear more about this. And then it's gonna be me, Alex and Jan, presenting you the latest news and hot topics in deep learning. And then, yeah, we can do more drinks, beers, networking, hopefully more food. Yeah, please take a seat, everyone. And I'll hand over to Valentin Borrico.
Thank you. Thank you. So this topic would be about multimodal learning and Google's approach to create one such model. So multimodal learning is about finding or creating a model that will learn different modalities and can have such features as getting input in one modality and getting output in another modality, or making transfer learning when one modality complements another one. So for example, when you learn to translate from one language to another, you can also complement learn kind of skills or weights to translate into another language. Then we have that, can we create such a framework of deep learning to solve a multimodal learning problem? Yes, we can, and there are different approaches to this. So there are restricted or deep Boltzmann machines, there are autoencoders, there are embeddings into joint space, and other approaches that can help us to do so. And this is an example of the Google's work. They created a model that can take, for example, an image and then to show the description of this image. And take, for example, the image and show the category, and you see the rest. So like the model is doing, one model is doing all of this. So it can be called multimodal learning program. So what we have, there are some examples of multimodal learning that already were created. For example, when you use restricted Boltzmann machine or deep Boltzmann machines, you can, for example, create a captions or learn the captions, like positioning of the caption and the image in the feature space or the hidden layers, so to speak. And approach to solve this is Boltzmann machine, so deep Boltzmann machine. It basically, like a neural network, I believe some of you already know this, but it's like a neural network, but it's a probabilistic model and it has connections both ways, so to speak, when neural network has this only one way. And in this model, we learn, we just simply maximize the probability of this function, the probability of the network. And it's called Boltzmann machine because this probability is corresponded to the Boltzmann distribution. So it's one approach that was used to make correspondence between images and text. Then also there is another one, it's embedding in the common space. When we embed the images and the corresponding text, so in this case, for example, a ship and a description that a ship is sailing in the ocean. And we embed them, so kind of multiply with metrics, so to speak, or with a series of matrices. And we then have a scoring function that measures the similarity between them. And we maximize, so to speak, the positioning of the similar images and text and try to minimize the false, so to speak, the false correspondence of the false text and to the right image. So it's like embedding in the common space. Then we also have, we can use the Kullback-Leibler divergence as a metric to reduce the distance between the audio and the image frames. So in this case, it's SoundNet architecture. I can also show you a video if I'm allowed to do so via internet. What they did, they took a video stream, and they took already existing CNN. They took the features of the CNN and learned the network that way, that the Kullback-Leibler divergence, it's basically this formula. It's the distance between two probability distributions. They try to minimize this distance to create a network, so to optimize the network this way that the distance will be minimized. And when we do so, when we minimize the distance, so here, for example, it's minimal, as we see, for example. When we minimize the distance, in this case, we can achieve the following result. Can I show the video here? Via internet. If I can, then I won't show. Can I show video, like just example of the model? Yeah, with this link. So here it's still not the models that I'm describing, but I'm just showing showcases of the already created models, multimodal learning models. Here they will show that when they get the audio input, they will try to kind of find which entity will correspond the best to the given audio. So for example, yeah, one of these videos working with it. No, one of the upper ones, yes. If it is possible to see. Okay. So it's hearing the audio stream, and it's kind of saying which text is corresponding or can be corresponded to this audio stream. Here it said sky, and then stage indoor and fountain. And another one is, for example, so in this case it says it's art gallery. Okay, who knows? So those are examples of already existing multimodal learning models. And if we go to the models that was created by Google, it has a fancy name, one model to learn them all. It was trained on the following data. It's Wall Street Journal speech corpus, it's ImageNet dataset, then image captioning dataset, and then parsing dataset, and then some translations dataset. The model's architecture includes attention, series of DeFi separable special convolution blocks, encoder, decoder, and dot product attention. This model has special type of convolution. It's called DeFi separable convolution. It allows to, and also with Bayesian normalization. So it allows to have a computation of a CNN to allow it to compute the convolution faster, because we don't have like 3D blocks. We have only 2D blocks, 2D filters in our convolution, and also we have Bayesian normalization. And here they also use attention that is pretty typical in such kind of models, encoder, decoder, when we kind of learn on sequences. They use attention to choose the right parts, of the sequence to apply the modality to. For example, in this case, when you would use no attention, for example, and when you would ask what is the color of the code, and when you get such an image, traditional question answering would say that it will analyze the whole image, analyze the question, and give the answer that is brown, which is wrong. And with attention-based, you find a code. So we have a kind of attention model or neural network that finds the code, and then judge the color and give you the answer, yellow. So this is a scheme of attention model. It's where we get inputs with LSTM, like memory, long-term memory units. When we get inputs, and then we put it through attention, that choosing, so to speak, the right parts of the sequence to compute. And then we also use decoder. And then we put back again decoder and decoded output and next input to generate a sequence. So like we make sequence-to-sequence learning. They also use mixture of experts layer. Mixture of experts, expert layer is using gating function, again some neural network, that is learning which weight, when we have, for example, different modalities or different experts that can learn our data, that can encode our data. The gating network is using the right experts for the right data, so to speak. And it's weighting, it's choosing the weights to weight the output of the experts. So it's basically like back of networks or back of experts. And so they have, for each modality, they have modality blocks. And modality blocks, they are, it's basically a convolutional step that is basic convolution. And then max pooling. So you know what is max pooling, what is convolution. And then they use the same kind of principle, so a series of convolutions for different modalities. They created the similar model to the joint image text space, so to speak. They encoding the input with spatial tricks, and then they decoding and generating a right sequence. So with all of this said, they show that their result on the top result of their model that is trained simultaneously on 8 different tasks or corpuses that were presented before is achieving 86% accuracy. Like, it's not as good as the state-of-the-art model, but still, like, they are trained simultaneously on different modalities. And also the Bleu score is kind of, it's the score of how good the translation model is. They're showing that it also like worse than state-of-the-art models, but still they do it simultaneously on different modalities. And I find it pretty interesting. And just to sum it up, the multimodal learning can be solved with different approaches. So this model is not the new one, but is more general one. So it considers more modalities and has more tricks that saves computational time and do, for example, batch normalization and attention and so on. And yeah, so I stated here. And the outlook would be is to learn or to look up more on the transfer learning as well as one-shot learning when you don't need a lot of examples, you need only one example to learn the representations. And memory networks, so there are also memory networks with memory states, and one can also use attention to find a right memory state or memory units to use to train the model. So basically it was it. Yeah. If you have any questions. Okay.
Yeah, let's open the floor for questions. Are there any questions about this part of our meetup, of Valentin's talk? Yes, please. Jan. Here we get our audience microphone.
Hello, thank you for your speech. I have such question. Can this approach be used, for example, for combination of processing and generation? For example, text processing and generation of some brief description.
Again, your question, when we...
Can we use so with the multi-modeling?
Yeah, I mean, basically, when we have sequence-to-sequence learning, we can use this model. So like when we read one text in... give me an example. So like one example would be to translate from one language into another language. So it can be used in this way. And also if you have one sequence and it should be corresponded to another type of sequence, it can learn it. Yeah. It can learn the right, so to speak, weight or representations.
Are there more questions? Yes.
Is there a way to enforce that each of those experts is somewhat different, or does the network learn it on its own?
Are the experts different, or?
Yeah, is there a way to actually, if I would train, for example, random forest, and each tree would be the same, then there's no point in training a forest. If I train this network where I kind of gate each of the experts, can I somehow enforce that each of the experts is learning something different and complementary to the others?
Yes, by using gating networks, you correspond the given input to the given expert, and it's learning the corresponding modality or the corresponding kind of functions that it has. And again, those are neural networks and not random forests in this case. So different types of neural networks with different convolution layers.
Nice. Another question from the audience. Alex, are you checking the YouTube channel? No questions there? Okay. Do you have a question? Yeah, then let's conclude. I mean, you're still here, right? After the next block.
Yeah.
If there are more questions, yes. You're open for discussions.
Yeah, sure.
Yeah, and we're gonna provide the slides to the people.
Yeah, sure. No
Okay,
problem.
good. Then let's thank Valentin again.
Thank you for the attention.
Thank you. And yeah, this brings us to the last block of today's 13th Vienna Deep Learning Meetup. Let's close this. And let's get back here. So I forgot to ask at the beginning, who of you is for the first time at our Deep Learning Meetup? Wow. Who can tell me how many % this is? Let's do the counter check. Who has been to our meetups before? Oh, yeah, it doesn't look that bad. So in the beginning, we had like 2/3 of regulars, and our aim was like to build a community that gathers and discusses and networks. Became a little bit more difficult as we grew, as I said, from 30 people to 130 something. We were here today. But yeah, that's nice. We're really excited about this, but it confronts us that we have a lot of new people every time, so we try to balance the talks not to be too challenging, but also not to be too much introductory. So we positioned ourselves as quite an intermediate to advanced meetup, just to mention that. We're gonna have later on somebody speak from Vienna Data Science Group about other meetups. But what we did in the course of developing this format is to add this section, hot topics and latest news. Because as you know, deep learning is evolving really, really fast. It's almost impossible, even for someone who every day deals with deep learning, to follow everything that's going on. There's a lot of research being put out, a lot of software frameworks, open source, different frameworks from bigger or smaller companies or universities. And then like these questions that we had here now. So it's sometimes little details that block your life or then can solve your problem. And that's why we built this community, because you can talk and interact with each other and then maybe help someone solve this particular problem just by this tiny little bit he was missing. So we're trying to solve this, and that's why it's really interesting. I want to thank all our speakers today again. So now it's up to us as the organizers, Jan, Alex, and me. We do typically this block of hot topics, but this, I want to stress this every time, especially as we have new people. We want to build a community, and we want not that we do lectures for you, we want that you interact and that you also help us find new topics, because of course we can't observe everything that is going on in deep learning in this whole topic of AI. So the call goes to you once again. If you find something really interesting, please let us know, write us emails, contact us on meetup.com or every other way you find. But let us know there's something cool out there, and we're open. Like, you can also just compile your 5 slides or whatever you want, come to the meetup, bring them on USB, or ideally send them to us before. And we include you in a block like this. You come up here and talk 5 minutes about the new topic you discovered. So we're still hoping that there's more participation from the audience. So this is also for people on YouTube now. You can also send us stuff. But for today, it's the 3 of us that compiled some stuff. It's a little bit more than usual, so it's going to be taking about 20, maybe 25 minutes, because it's been June since we did our last regular meetup, and as you may think, there's a lot of development since then. I will start this block. I was 2 weeks ago not even in World Summit AI in Amsterdam, which was a huge event, 2,200 people, you can imagine. Two-day event, really exciting, and I think it was a really cool balance because there was people like discussing new topics, like also this topic of when will we get artificial general intelligence, but then also some criticism about deep learning, about AI, what is going wrong now, what problems didn't we solve yet, is AI dangerous, do we need to be afraid of robots? So some people say yes, if you don't build ethics or any kind of rules that the machines will accept, we're gonna have some problems. We actually plan and discuss to do maybe another meetup evening like this one in our series to discuss more about these ethics and problematic things, because so far you have seen us as pretty much optimistic because deep learning is our everyday stuff and we really like it. But of course, we should discuss these more problematic things. Some people commented to me today also interesting topics. We will ensure that we talk about this more. So here's my takeaways from World Summit AI in Amsterdam 2 weeks ago. There were some really very high qualified speakers there, professors, but also from the big companies. And yeah, I mean, this is very simplified, but very summarized. I have a few more slides. This is the first one. So main takeaways. Okay, you know that AI is taking off, but we are not quite there yet. So some problems are narrow AI. They still need to be solved on a broader scope, especially this topic of, do we have truly intelligent machines yet? Most people say no. We need some machines that are more conscious of what they're doing and what they're deciding or recognizing. And this will take time. It's not like that we're gonna have super intelligence like in 5 years or so. But nevertheless, ethics and dangers need to be discussed now. And more than discussed, they need to be actually started to be tackled. So to build ethics for machines, but also implement rules and ensure, like, actually research on ways to, like, from the very start build this into the machine, so there is not like this super dramatic scenario is going to happen that some people depict beforehand. And then another topic, of course, was AI is too much narrow right now, too narrow, so we can solve very specific tasks like speech recognition, all these beautiful things you've seen, but it's not kind of combined. So the multimodal approaches, like Valentin just presented, they are a good start. They're going into the right direction, but there needs to be done much more. And then there was some criticism on deep learning, which is interesting too. So they say deep learning is actually the cause why we have such narrow AI systems. And in order to build a true, like, conscious AI systems, deep learning might be the wrong method. So we still believe deep learning is the technology of our decade, but there is some criticism it might be the wrong path to really get to something truly intelligent. So this is a question mark that we would like to discuss in the near future. I like this statement somehow. I mean, of course, nobody can prove it, but Stuart Russell, who is a professor at University of California, Berkeley, it was his talk that was quite critical, but he also mentioned the value created by AI is or will be bigger than the GDP of the entire planet. So this is like just a statement to say how big and how huge this development is actually. I mean, of course, nobody can prove it, but it's just to say there was another curve that is like this exponential curve, and it's that we are now in this angle where it starts to become exponential. So we are only at the start of this topic to really take off. I mean, we see it a little bit with the development of the number of people at this meetup, but also many people think we're just only at the start. So he had a quite critical talk. He has 2 really good TED Talks on YouTube. I really recommend to watch these, but the summary in Amsterdam was, the rapid progress in AI is of course impacting the entire society. So there's all these topics of how many people will lose jobs due to automation. But then again, also there's a huge opportunity for many people who are in this domain. So a whole lot of words can be spent on this topic alone. And then of course there needs to be a little bit regulation. So one part is ethics and the research of AI, thinking and building more ethically proven methods for this, the way we're going to in machines and machine learning and AI. Then related to the first part, we need to prepare for major economic disruption. So it's changing our life and the life of many people, probably all of us, dramatically in the next decades. Yeah, and then there needs to be the theory and practice of provably beneficial AI. So it's a good end statement, but of course you can discuss here a lot. So I recommend to watch these talks. So this is one, sorry for this image quality, but it's actual photos I took from the slides there. I have to excuse also for the people who did the, excuse to the people who did these slides originally. I should put credits here, but it's missed. I think this is one is from so green and red, so what we have, you know, deep learning has contributed a lot to that we have really good working speech recognition systems, but it's mostly when you have a room, it's native speakers, the environment is quite okay, not too noisy. Similar in image recognition, when you know the number of objects or the specific tasks, natural language understanding, and so on and so on. So his statement was, these things, it's this narrow AI statement. So these things work when you train them on a particular task, and in the ideal circumstances, they work really fine. If the circumstances are not so ideal, like background noise and so on, you have already a problem, or with languages they were not trained on. So the red part is we are far from actual perfectly working systems like conversational interfaces, really automated scientific discovery, or really automated medical diagnosis. So we can assist, for example, doctors today, but a machine cannot tell you whether you have cancer or not, or shouldn't tell you at this point. Yeah, same with cars. We hope to see really working cars soon, but we have to expect in the beginning they will not be perfect as humans. One major takeaway and point there was, so right now we're in a world of recognition. So you can also say classification. We train supervised convolutional neural networks or other neural networks, and it's always about categorization, recognition. And the whole topic should shift into reasoning. So machines should be able to reason about the things they see. It's just not possible right now. I think Yufeng also mentioned it. We can categorize a cat and a dog, but the machine doesn't know it's a cat or a dog. It's just spitting out that label because it was trained to wire some connections to tell you it's a cat or a dog. This is exactly that topic, and we need reasoning, attention, memory. So it's, as you see here, a lot more to be done. The multimodal learning we've heard about now, it's quite early in its days, and there was one topic, a particular talk that was about deep reinforcement learning with memory. You can look that up, maybe we'll dig into this in a future meetup, but just to mention it here. And here on the lower right you see perceive, reason and act should be the way to go, and not just recognize categories of objects. Then, I think this is already my last slide. These ethic questions or other questions was quite a refreshing discussion. I liked that because it was not only about the benefits of AI, but talking really about the problematics, like biased AI. There are many examples about the web, about racism and other things. So here it's also about algorithmic equality. There is discussions around this, but it's really tiny so far, so it should be much more about these topics. Then I mentioned it, reasoning and understanding intent, also of people, should be important. And then, I didn't put the speaker now, uncertainty in AI was a very interesting topic, because now, as we said, we train these systems, they will spit out the category cat or dog, or in the case of self-driving cars, they will spit out passenger or trash can or something and decide whether it can roll over it or not. But the AI system should actually know when it's uncertain, should know when they don't know, was a major statement at the event. So this uncertainty should be really a future topic to be considered, especially when we talk about things like self-driving cars where people can come into danger. And then the final talk was about the power and limits of deep learning by famous Jan LeCun. And yeah, a lot of things told in this talk, but basically it was also about the limits of today's deep learning approaches and how to solve them. I guess you can find plenty of his slides and talks online. I just wanted to do a brief recap on what was discussed 2 weeks ago at World Summit AI. Yeah. So by that, I hand over. It's going to be the three of us, now Alex and then Jan, doing these hot topics. And yeah, Alex.
Thank you. Yeah, I will present some, in the next slide, I will present some hands-on tutorials where you can try deep learning experiments on your own. And the first one is deep learning on Apache Spark. So if you don't have a CPU, but an Apache Spark cluster, which is apparently, surprisingly, there are a lot out of there. This is a very nice example which shows you how to use a pre-trained VGG16 model on a Spark or Hadoop cluster, and it introduces you to deep learning for GAs. So it's a nice tutorial to use Java for deep learning, which is kind of the main programming language in engineering. And to stay with Hadoop and Spark, last week there was the natural language processing library introduced. Natural language processing is where you do text processing. And this library has some very convenient features. If you're doing NLP, then you will know about tokenizer and stammers. And so you can now, previously you had to use pre-processing on a different platform. Now you can do this directly on a Spark cluster. To stay with NLP, if you're interested in NLP, there is a very nice crash course. It introduces you to text pre-processing, text modeling, visualization with using t-SNE, and it's a good tutorial. It introduces you to Python libraries like NLTK, which is the standard library for natural language processing, Gensim, which was one of the first libraries to implement word2vec, and sklearn for t-SNE, visualization, and Bokeh, which is a very nice interactive visualization and charting library. You can do go with the mouse over the chart and draw and zoom and pinch zoom, and it's quite nice. So if you're familiar with word2vec, this is an algorithm which learns semantic relationships between words. And like here in this visualization, it learns that there is some semantic relationship between horse, cow, and pig, and cats and dogs. And it even learns kind of relationship that Paris is a capital of France, and there are some, then you can do some semantic transformation that when you subtract France from Paris and you add Italy, then the resulting vector is more close to Rome than any other vector of your collection. And these relationships, they're kind of independent from the language. So in the field of cross-lingual word embedding models, you use a model trained in English and apply it to a different language, and you kind of get the same relationships in the other language. And if you're interested in this, there's a really well curated survey that was published last week. It was written by Sebastian Rude, who is currently pursuing his PhD on this topic, and he has also a very good blog where he regularly posts introductions to various fields of deep learning, to natural language processing, and also a lot of tutorials and IPython notebooks. Yufeng today already mentioned how to use matrix factorization. This is an algorithm, a method used for recommender systems. And the example was this one where the chicken wings and the waffles were recommended to possibly pregnant women. So this tutorial is really going into deep. It's a very excellent tutorial. It explains every step that is needed to do to create a recommender system, every little aspect of matrix factorization, and how to use MXNet to create deep matrix factorization models and to apply this on the Netflix movie dataset and to recommend movies to your users. If you're like me, that you understand algorithms and papers more precisely if you see the code, then these 3 tutorials are for you. The first one codes a neural network from scratch. It implements a fully connected layer in Python. It introduces you to forward and back propagation and to the prediction step. This is a well-made tutorial. And the second one introduces you to long short-term memories, which are recurrent neural networks. And they also show you an implementation using NumPy. It's also well made, and you really get into the deep the implementation, and you really get a good understanding of LSTMs and neural networks. And the third blog post is a collection of blog posts, papers, tutorial, PhD and master theses, all you can wish for if you're really interested in recurrent neural networks and LSTMs, so you get all the information there. If you're interested in blockchain, there's a very well-made tutorial how to connect blockchains with deep learning. It's an example where you use smart contracts and machine learning to implement a chat client, and you can transmit messages to the blockchain, and a smart contract is triggered where a pre-trained neural network tags the image and tags the text, the message text, and this information is stored again to the blockchain. It's a well-made example. So if you're interested in overly complicated database systems, yeah, well-made. This is quite redundant because Tom already talked a lot about this. DeepMind announced that they initiated an Erste Group where they discuss and work on problems about ethical and societal questions raised by artificial intelligence. That's, yeah, quite, Tom already mentioned there are quite a lot of fears concerned with artificial intelligence, and we definitely need to start talking about this, because usually we had science fiction, so we used to be talking about all this. We know from Jules Verne that flying to the moon is good, and from Terminator we know that self-shooting robots are not good. But we haven't talked about is it okay, is it ethically okay that black boxes, that artificial intelligent black boxes judge about, are we allowed to get credit? Are we the perfect person to get this job? Or about to use artificial intelligence for law enforcement, for public observations, or for predictive policing. Yep. So I hand over to Jan.
Okay, so great that you ended with public observation and surveillance videos. So I picked together a few papers from the last month, some from the last week, and some from the summer break that I found interesting, that give you pointers in all kinds of different directions. So this is, we often talked in the meetup about GANs, generative adversarial networks, that are able to generate images, and then often there was a question, why would you want to generate images? And here's a paper where they took a face recognizer, or face detector, and combined it with a neural network that was able to render faces, and then they used this to sort of anonymize surveillance videos. So sometimes there are public spaces being observed, and you don't really need to preserve the identities of all the people that are going in there, because you're kind of invading their privacy. And often it's enough to just, if you want to see if there's something awkward happening, you don't need to constantly monitor all the faces that are in there. So they replaced the face by surrogates rendered by network. And that preserves more information than simply pixelating the images or blurring them. And another interesting example is when we listen to each other in like noisy conditions, it helps if we can see each other's face, and especially the lip movement, then we are able to better understand the other person. And here some people, they figured, maybe we can also use this in a neural network. If we have some noisy speech here that has a lot of background noise, but in addition we are able to observe the lips, then maybe we can use this information to get a better, cleaner voice. So they showed that by including the lip movements, you get a better reconstruction up here than if you just use the noisy voice and try to produce a clean voice from that. But actually, if you look in the results in detail, so they looked a bit at what the network does, then it's mainly using the cue of whether the mouth is open or closed. So whenever the mouth is closed, it can just silence everything, so there will be less noise. And yeah, but it's still a nice idea, I thought. Then another nice idea. I'm not sure if they are actually the first one who did that, but you know that GoogleNet has multiple classification layers in the network, which they used to be able to. So this is not GoogleNet. This is just some toy example they put in this paper. They put some extra exit nodes with which all have to do the classifications for object recognition. At each exit, the network has to produce the correct answer. So they did it to get a better gradient information for the earlier layers in the network, so they don't have to rely on the information going all through the deep network. They get some extra information from here and here. And what they did in this paper is to use this kind of architecture for faster inference. So if the prediction here is already very confident, as measured by the entropy, then they say, okay, this is our prediction, and they don't evaluate all the other layers. And that's a nice idea to make networks faster for deployment. So in this case, they achieved about 2 times speed up. And also for deployment, there's an old trick from 2015, where when you have a very big neural network and you want to deploy it, you can train a smaller network to reproduce the outputs of the large network for each input example. This way the large network will be able to learn a good function, and then the small network is trying to just copy the function from the large network. And the the key thing is that the small network is trained to also reproduce the exact probabilities for all the classes that are not the true one. So if the true label is a husky, then the network is also trained to reproduce the probability for other breeds of dogs, for example, and also for whatever palm trees and whatever is in the data set. So by this it will learn the same kind of generalization that the large network learned. Now this requires access to all the training set. So what they did in this paper is they tried to take the large network and reproduce the training set from the large network, because it has a lot of weights and it has stored a lot of information about the training set. And they added some side information to make this easier or make this better. And they showed that it kind of works. It doesn't really work as well as training on the original training data when you train the small network, but it works, yeah, a little bit. So it's also a nice idea, I found. Then this is, I think, more of a joke. So this is a blog post by OpenAI. When you have a deep neural network and you don't have any nonlinearities in between, then it can be reduced to a single layer linear network, because if you stack a lot of linear operations, then the end result will still be a linear operation. Now they saw that in the standard floating point representation that is used, there's, if you zoom in on the order of 10 to the minus 38, there's some gap. So this is the smallest number you can represent, and then there's a lot of numbers between the smallest number and 0 that you can't really represent unless you use denormal numbers. But if you exclude that, then all these small values get clamped to 0 when you get this as a result. So actually you have some nonlinearity built in to the floating point processor in every floating point processor that follows the IEEE standard. And now you can't really train a network with this fact using backpropagation, because then the library would have to know about this fact. But they showed if you use evolutionary algorithms, then you actually can train a network to exploit this free nonlinearity to get good results on MNIST, for example. And so the practical use is probably very limited. I mean, it's like you have a free nonlinearity in some hardware that is very widespread, but the nonlinearity is usually not the bottleneck. So I think it's more like a joke, but it's very fun. So you can train a deep linear network and it exhibits nonlinear behavior. So then this is also from last month. We've been following the text-to-speech methods over time, over the last few months. And so we previously discussed WaveNet, which was released in September 2016, and Deep Voice 1 by Baidu in February, Tacotron in March, Deep Voice 2 in May, and now, I think last week or the week before, Google DeepMind announced that they are now using WaveNet in production in Google Assistant. And they improved a lot over the previous iteration of WaveNet. The previous one was very slow. So WaveNet is a model that is generating audio sample by sample. And if you can condition it on like the kind of phoneme you want to, and the pitch you want to produce, so you can use this to produce speech. And they sped it up a lot, and also they improved the sound quality. They increased the sample rate and the number of possible amplitudes that the network can produce. And they get now really convincing results. So if you follow the link, I will not do this now to save some time. You can listen to some examples. And they actually sound a little bit better than Deep Voice 2 and Tacotron. they ask some humans to rank the quality of the voice, how natural does this sound. And if you give them actual human voice, it scores at 4.6. And then you see all the models here. So these are models that don't use WaveNet. They didn't say what it is. So there's no research paper on this yet, just a blog post. Also, you see it's not really clear where this chart starts. It's definitely not 0. But yeah, they see that they get some good improvements from using WaveNet on this. And just as a side note, the University of Hamburg last week released a corpus of Wikipedia articles read out by humans, with aligned timestamps for each word and also sometimes for each phone. So I expect that this will make it much easier for research outside of Google and Baidu to create such text-to-speech systems in the future. Then there's AlphaGo 0 that was also released last week. It's a Nature publication by DeepMind. This is the ELO rating. That's a rating system used for chess and also for Go. And this is the new AlphaGo 0 that they trained over the course of a couple of days. And after about 3 days, it beat the version of AlphaGo that beat Fan Hui, and then the one that beat Li Sedal. And in the end, also another one called AlphaGo Master. And what they did, so AlphaGo in general consists of 2 networks. One network that sees the board and tries to predict which move to make next, and another network that sees the board and tries to predict who's going to win this game. And then they combine this with the Monte Carlo tree search, which was used by many Go and I think also chess engines before, to get some kind of look ahead. So it's kind of using the network to predict some moves that might be good and then evaluate what kind of board position will result from this. So it's like thinking forward a few steps. And the main novelties they did now was instead of using 2 different networks, they used a single network that is very large. So it could use some common representation, because predicting who's going to win and predicting what move to take may require a similar understanding of the board. It doesn't use rollouts in the tree search, which means when you reach a node here, it just uses the value network to evaluate who's going to win, whereas in the previous network version, they used some kind of fast rollout where you just try to predict moves as fast as possible until you reach the end of the game, and then you see who has won. And the main novelty is that it's completely trained from scratch, whereas the previous one was trained on human games before to predict what a human would do in what kind of situation. So it improved over the previous system and over probably all human players now, just from scratch. And they used the tree search in the training, whereas before they would, so after a while they train AlphaGo against, or they play AlphaGo against itself, so to say, and before they used reinforcement learning just to train the network to win against itself, and now they use the predictions they get from the tree search about which moves to take, and also the end result of who has won to train the policy and the value network in each step. So they get some extra supervised information from that. Because usually what you get from the tree search is much better than what the network would predict alone. All right, then this is something more theoretical. So a common problem in deep learning and also in recurrent neural networks which can be seen as a very, very deep network, is the exploding and vanishing gradient problem. So when the weights are too large or too small, then the gradient, when you backpropagate through the network, will either get very large and large and larger until it kind of explodes, or it will get smaller and smaller and smaller until there's no gradient left. And one of the first solutions to this, actually the first solution was to pre-train networks unsupervisedly. The next one was to try to scale the weights in a way that the variance of the data when you propagate through it is kept at the same level. But the problem is that even if you scale the weights correctly, these random weights have very different singular values. So there are some singular directions or some eigenvectors or some directions in which they blow up the variance and some other directions in which it shrinks the variance. So the overall variance stays the same, but the matrices are very ill conditioned, which is bad for optimization. So what Sachse proposed was to initialize the weights as orthogonal matrices, so all singular values are 1, or at least all eigenvalues are 1. And then the remaining problem is this, of course, only holds at right after initialization. When you train the network, this can change again, so you can get ill-conditioned weights again. And people propose to parameterize the networks in a way that the weights will always stay orthogonal. But still there was a problem that the way they did it was very costly and used computations with complex values, which are not well supported in much of the software frameworks. So what these people did was to use a simple transformation that can transform a skew-symmetric matrix, which is kind of a matrix that is symmetric but has all the signs flipped. And with this transformation, if you have a matrix like this, you always get an orthogonal matrix. And also you only need half of the parameters because you only need to store the upper triangular values, and then you copy it and invert the signs, and you get a skew-symmetric matrix. So this allows to train recurrent networks that don't have the vanishing or exploding gradient problems very efficiently. All right, and then these are just some pointers on more of the theoretical part. So David Duvenot said, and that's something I really found a good way of describing it, that what we are doing right now in deep learning is like engineering before we knew about physics. So there's one paper that says, hey, I made this bridge and it stood up. And then there's another paper which says, I made this bridge which is much longer and it fell down, but then I added pillars and then it stood up. And then pillars become popular and everybody starts using pillars. And then somebody discovers arcs and so on. And that's about how deep learning research seems to work right now. So you can replace these pillars with dropout or batch normalization or some initialization scheme. So there are some thoughts behind that. There's some reason why we think pillars may help, but in the end it's all very empirical. And there's some work trying to improve on the understanding, on the physics behind deep learning, mostly on why do deep networks generalize so well. And these are just two of the papers from last week or the last 2 weeks that you may want to look into if you're interested on the mathematical foundations. Oh yeah, then two things about software. So one very sad thing that Theano will be discontinued after the next release, and that's special because Theano was one of the very first deep learning frameworks. They were the first to introduce this concept of building computation graphs and optimizing them and compiling them, so run them on CPU or GPU So they invented a lot of features that have now become widespread, and that's also one of the reasons why they decided to stop now, because now there's a very large ecosystem of a lot of open source software for different purposes, and it doesn't really pay off for a university to try to compete in this field anymore. It's not really a scientific endeavor anymore to maintain a deep learning framework, so they decided to stop it now. So we will also stop developing lasagna after Theano is discontinued. But now there's a replacement, not really, but I found this one. It's a deep learning framework in JavaScript, which allows you to run networks in your browser and actually also train them in your browser, and it runs on the GPU. So this it's not really a replacement for any other framework, but it opens up some new possibilities. And there's not really a way for a web browser to do general computations on the GPU. There's WebGL, which is meant for graphics. So what they do behind, or some libraries they build up on, is to convert the input data into some image, and then run a pixel shader on the image that does the right thing, that does a matrix multiplication in the end by doing something with the color values, and then they copy back the result. That's actually how the first deep learning libraries on GPU worked, before there was CUDA and OpenCL and so on stuff. Yeah. So now we have some announcements by Tom. Thank you.
So it's actually not announcements by me, but we have Andreas Rath here. Yeah, can you come up? So before I hand over the microphone, generally, yeah, it's just for this last section. We enable people who look for other people for jobs, projects, and so on. 1 minute or so to speak. Just make an, I mean, you can do that in the networking, of course, but if you want to reach all our audience and just announce that you have a job opening or so on, we can do this very quickly. And here we have two things from Andreas. Maybe you want to talk first about Dualista.
Yeah, very briefly. Hi, everyone. Dualista is a program started by INITS and Tech Group is that over there. It's kind of a job where we have two jobs in one job. So 50% you work for the tech group and 50% you work at the startup. So you have the security of a startup on the one side, the security of the tech group on one side, and the fun and innovative environment and inspirational environment on the other side. So, and if the startup fails, then the tech group will employ you 100%. So it's basically risk-free and a lot of fun. There are a lot of startups in INITS, same as Ondevo, which is my startup, and which we are participating in this program. So if you're looking for a job with security and innovative fun and the risk, then you can have a look at Dualista. What's the next one? Oh yeah, we talked a lot about software and algorithms and everything. We decided to build our own Ondevo Dream Machine. So maybe one sentence what we are. Ondevo stands for On-Demand World. We are building a digital assistant, so a conversational interface to bring together consumers and service providers to find very fast a match for finding your next hairdresser or for finding your next massage therapist in the next 90 minutes. For that, we use, of course, natural language processing, a lot of machine learning. We also use Google TensorFlow. And we are building our Dream Machine, basically on the 3rd November. So we have 3 spots left. If you want to get a little bit dirty in terms of hardware and screwing things together, then please talk to me in the break. Happy to invite you with pizza and beer to our deep learning Dream Machine building. Maybe some specs. 40 times GPUs, 2 graphic cards in there, 128 gigabytes of RAM, 1 terabyte SSD drive, super fast, super cool, and the tower needs to be built from scratch. So bring your screwdriver. Thank you.
Thank you. So yeah, maybe before you destroy your own computer with the new GPUs, you can help Andreas doing it. Okay, more announcements. So one thing is that we recently had a meeting with other meetup groups in Vienna. Because there is a lot like R meetup, Python, data science, and so on, and we have now the aim of avoiding like overlaps with the dates and so on. We want to be more aligned with other meetups, and that also means like discussing a little bit the target groups, like who do we address with this meetup. What do the other meetups stand for? Who do they target? And like all these different formats. We're thinking right now of how to bring that message better to the people. Like maybe setting up a website where we describe the different meetups. This is still a work in progress. But now I have Wolfgang here from the Vienna Data Science Group to tell you a little bit what is the Vienna Data Science Group and the meetups they're doing.
Hey guys, thanks a lot, Tom, and thanks for surviving that long. I mean, it's now what, 4 hours or whatever, and a lot of you are still awake, I think. So I keep it very, very briefly. Who are we, and what are we aiming for? Yeah, we are aiming to promote the knowledge about data science. Well, that sounds very broad. Let's put it like that. We are an NPO, so we are a Verein, and we are really aiming also to bring some sort of, let's say, self-consciousness to the community. What does this mean? I think data scientists seem to me the most humble persons on the planet. Why? Because I think the first thing I always hear from data scientists is like, I don't know that. Or, no, I'm not a data scientist, I'm just fiddling around with TensorFlow or something like that. And this was one of the reasons why we founded this some years ago now. With a diverse member base, I won't bore you with that. We started with an international scope because we think Vienna is cool, but well, it's Vienna and it's nice and it's good to live here, but the world out there brings so many inputs. So we have members from France to Bulgaria now. So how do we do that? I mean, yeah, you talked about we are doing a meetup as well, but if you want to get your hands dirty, I really like the sentence before, really. Then come to our data science cafe, which is much, much more hands-on, because I really like the sentence about building the community, and I really like that so many people are here now. But the point is to interact and to really build a community of people who actually build something from code to knowledge and so on. It takes much more. So we described it very, very in detail on our website. In one sentence, come there with your laptop and get your hand dirty. There will be mentors and very, very cool things, and I think also cake and coffee. It will be this Friday the first time, so I will display then the data and the link. Networking, yeah, we are doing a lot of these things. If you want to get in touch with us, we are, I think, on every network possible. But our meetup is not as many people as here, but I would say I really liked one of the sentences here. I think it was in the middle of your slides. It somehow works, and I think this is the goal here, to make it work somehow. Thanks.
Thanks, Wolfgang. So this is an invite to also look by, take a look at the Vienna Data Science Group and the Data Science Cafes. So now, thanks for bearing with us really those long hours. We're really at the end now. So this is the moment where I thank again our sponsors of tonight, the Erste Group, who hosts us at this wonderful venue here and provides drinks and snacks. We thank also all the people who are watching on the stream. Until now, it's also been a long time, so thanks for bearing with us and watching this stream. As we said, it's a premiere for us. And this is thanks to our partner Streamed, who have a lot of people here tonight to make this happen and solve all the technical questions around streaming. The whole evening, the recording will be available also on the link here. We're going to post those slides and probably all the others on our Meetup group as usual. And here I invite you to our next Meetup, which is November 20th at A1 Telekom. The topic is evolution of image search at Setsnam. It's a really big player in the Czech search engine market. And of course, like our other guests today, they also have a lot of problems around search, especially searching for images. Very interesting topic. So it's combining image search with word embedding, a topic that we've also heard a couple of times today. So come again, new location as always, this time A1. And actually the speaker of next time, Lukas, is here tonight. Is he here still? He's raising his hand over there. So if you want to get a preview or a little bit of idea of the next time's talk, you can talk to him. And yeah, thanks also to Jan, Alex, and thanks to all of you. Now let's head over, have more drinks and more chats. Thanks to all of you. See you next time.